Hello, and welcome back to my next webinar on C++ Standard Template Library by Example. Today, we're going to return to our focus on C++ containers, starting with our discussion on the ordered associative containers, including map and set. What we'll do here is we'll begin by looking at the source code that you can find to download the examples I'll be covering, and then we'll begin covering the examples themselves. So without any further ado, let's go ahead and get started. You can find the source code we're going to be covering today in my C++ folder in my GitHub repository in the STL-S-05 subfolder. And we're going to start by taking a look at some of the introductory parts here. So let's go ahead and look at my interactive development environment. This particular file isn't really a program. It's just some documentation explaining what the concepts are behind ordered associative containers. These are containers that support efficient insertion, removal, and lookup or find operations of values based on various keys. These containers we're going to talk about all support the insertion and removal of elements, but they differ from sequential containers because they don't allow the insertion of an element at a specific position or a specific location. Instead, it's based on the value that's associated with a key. After the element has been added to the container, the key itself cannot be changed. It's effectively a const. And the reason for that, of course, is pretty obvious. If you could change the key, that would mess up the ordering. Of course, you can remove the element and its associated key. There are 4 associative containers that we're going to be focusing on here. These are the ordered associative containers. They're basically divided into 2 categories. There's sets and maps. And within each category, there's individual unique versions, like a set, versus versions that can have multiple keys with the same value, which are the multisets. So for sets and multisets, only the keys are stored, and you have to have some kind of ordering relationship defined in terms of the less than operation. But there's all kinds of ways to arrange to do it with other orders besides just less than. If the values are very simple, things like numbers, then obviously you just use the less than operation on the numbers. If they're stored by alphabetic order, you can have them ordered that way, lexicographically, or if they're user-defined containers, then they have to have the less than operation defined. And you can take control of that and control it in the way that you see fit. For maps and for multi-maps, there are keys and values. For a map, there's a unique set of keys. For multi-maps, there are potentially duplicate keys going along with the values associated with them. And these are basically pair associative containers. And we'll see that there's a pair class that's used for various things in the STL ordered containers. The keys can't be changed by iterators once they're assigned. You can, of course, erase them, but again, you can't change them because that would mess up the ordering in the map. Under the hood, these ordered associative containers are implemented as binary trees, and they use a red-black tree implementation. And basically, there's some optimizations that can be done because of the way the trees are laid out. We'll talk about those as we go through some of the examples. You can have your own associative containers you might want to build with some other abstraction. You might want to have some kind of a tree structure organized as a 2-3 tree or an AVL tree or some other data structure, which would be good as a way to learn more about how to implement these containers. And of course, if you build your associative containers using the same APIs as the ones that come pre-built with C++, then you can go ahead and use them with all the predefined STL iterators, algorithms, and various functors. You can use containers for all kinds of things. You can think of ways of mapping keys to values, and I'll show you some really cool examples as we walk through the various sub-lessons that we're going to cover starting today. We'll probably only cover a few things today, and then we'll pick this up and keep going next week. All right, so let's go ahead and actually look at some real code now. So let's open things up and see what our first example will be. So this example here is going to demonstrate several usages of the C++ STL pair template. Now, I've shown you some pair templates before, but they were really just stripped down for my purposes to illustrate a few things about stuff like passing parameters by reference versus passing them by value and so on. But now we're actually going to look at the real legitimate official STL pairs. And we're going to do a bunch of different things with these. First of all, let me show you a little helper class I defined called a point. And this is kind of a fun concept. So a pair is very important to STL. The associative containers typically are used to bind keys, which are the first elements in a pair, with their associated values, which are the second element in the pair. And you'll see that there's various ways you can manage and manipulate these pairs. There's actually a class called pairs, we'll see here in a second. And this is used in the construction of maps and other associative data structures. So I'm going to use the pair class to create a point class. So here's the point class. And this point class is going to be implemented using a pair. And we're also going to use this to show off some other cool things as well. So here is the constructor for the pair, which you can see it takes X and Y, which are templates of type name T1 and type name T2. What that means is we can have T1 and T2 be different types if we so desire. Now, for this particular case, we're going to use a pair as the implementation artifact to define a point. And the point is simply going to be these two data members, T1 and T2, which are references. So we're going to get a chance to see how you initialize a reference. So what's a reference data member? Well, let's take a look and see. So you can see X is a reference and Y is a reference. The implementation of this is going to be implemented by an STL pair. And so you can see I have a pair object, it's a data member called pair underscore. Now, because point is a template, we have to include the source code. So let's come up here and we'll take a look at the source code. So here's the constructor for the pair. And this particular constructor, as you'll see, is going to be also used to illustrate the concept of move semantics, which is a really cool feature added in C++11 that makes it possible to optimize move semantics, which heretofore would have been somewhat expensive, and we'll show how that works. So here's what the constructor is going to do. It's going to initialize the pair data member in the base member initialization section. And I'm going to use this move macro, and we'll see what the move macro does for the moment. For the moment, let's just pretend like the move macro is empty and does nothing. So what this will do is this will take parameter X, which is passed by value, and parameter Y that's passed by value, and we're going to go ahead and store them in our pair. So that'll get copied using the copy constructor, of course, into pair. And then what we're going to do is we're going to initialize Y and X, which are references, and we're going to initialize them to pair first, which is the first object in the pair, and then pair second, which is the second object in the pair. And because these are references, they're initialized, they have to be initialized in the base member initialization section. And that way we can refer to them as X and Y as opposed to first and second, which maybe makes more sense for a point. Okay, we'll come back and talk about the move thing in a second. That's going to be really cool. Another thing we're going to do here is we're going to have our simple string. We've used simple string before just to have a class that's going to differentiate between pass by value using copy semantics and pass by value using move semantics in C++. This class also demonstrates the so-called rule of 5, which supplants the previous rule of 3. So if you go and look at the rule of 3 at the Wikipedia link here, you'll see that the rule of 3 was the original description of what types of methods you should always define in a class. You should have constructor, a copy constructor rather, assignment operator, and a destructor. With the rule of 5, which we're going to show here, in addition to the copy constructor, the assignment operator, and the destructor, we're also going to have a move constructor and a move assignment operator. And we'll get a chance to see those things as well. In fact, you can kind of get a glimpse of them here and here. So we'll talk about that in a second. All right, so armed with that as the background, here is our main program, and we're going to run it and do some things with it to illustrate how it works. It's really fun. So the first thing we're going to do is we're going to make ourselves a point of two ints called myPoint, and we're going to give one int x being 100 and the other int being y equal to 200. And then we're going to go ahead and print out myPoint x and myPoint y. So I think you have a pretty good idea of what that's going to do. The next thing we're going to do is we're going to define another point, which is kind of a funny point. I'm going to call this book chapter 1. It's going to be chapter 1 as a string, and meet the C++ STL as the Y parameter. Kind of a weird point, but you get the point. So what we're going to do here is we're going to print out book chapter 1 field X, which of course is a reference, that'll get printed, and book chapter 1 Y, which also gets printed as a reference. The next thing we're going to do is we're going to show a point that's got two different values. We're going to have a string and a void star. Here we're going to pass in the string mynum, and we're going to pass in the void star as some, what maybe like a pointer, which is going to be assigned using the reinterpret cast. So we're casting this number into a void star using the C++ reinterpret cast to make that work in a type-safe way, as type-safe as you can get when you're doing casts. And then the last example is the most interesting one. This is going to be a point that's got a pair of simple strings. So this will get us a chance to see what's going on under the hood. So in this case, we're going to have one simple string being chapter 2, and the other simple string being meet the C++ STL associative containers. And once again, you'll see this funky little move macro showing up here, and we'll take a look and see what that does in a minute. Now, the first thing I'm going to show you is initially, if we go over here, we're going to set move initially to be nothing. So no move is defined at all. So when I run this program, which I'm going to do now, you'll get a chance to see what the output is. And this will be very interesting, I think. All right, it's building. It's taking a little while to compile, and there is the output. So you can see my point X is 100, my point Y is 200. That makes perfect sense. You can see book chapter 1, X is chapter 1, book chapter 1.Y is meet the C++ STL. That makes sense. Then we print out mynum, and the number that we put in is the next one. That makes sense. And now things get kind of interesting. If you take a look here, you can see that this is what's used to create the point using the pair, using the regular copy constructor semantics. So if we just go back over here for 1 second, if you take a look at what main is doing, you can see that we're giving it a simple string with a const char star, and that of course is what's going to trigger these calls here. Let's see if I can split this a little bit better. There we go. So that's going to be those calls. That's going to be the constructor that creates a simple string from a const char star. And then you're going to see, if we go over here to point, you can see how we're going to assign X here. And so this is passed by value. And so we have to go ahead and basically do this value-based copy. So we're making copies here, and we're copying those things in after the object is created. That gets moved in here. And then there's a destructor that needs to get called because we passed it by value. And so you can see there's a fair amount of overhead. And if you go and look at simple string and you take a look at its copy constructor, you'll see what the simple string copy constructor does is it goes ahead and it makes a dynamically allocated copy of the right-hand side. So it actually had to make a full-blown copy. So you can see that that particular implementation is going to be non-trivially expensive. The compiler was able to optimize a few things away here, but by and large, we had to make a full-blown copy, and we had to call the destructor to free things up. Now what we're going to do is we're going to go back over here, and instead we're going to change the definition of the move macro to be the std::move method. So let's go ahead and save that. And now what happens when we actually compile this code, and of course when we run this code, is that this move is going to be turned into STDMove, which is a really cool method that's part of standard C++ that will perform move semantics instead of copy semantics. And likewise, if we go over here, these moves will be turned into STDMoves. So let's see what difference that makes when we run our program in terms of the operations that it performs. Now, as you'll see, this is really not going to affect anything except the code down here. So you can see what's happened here is before we had copy constructor calls and full-blown destructor calls that had to free up memory that was part of the copy process. Now, all of a sudden, we've got different calls coming out from simple string. Instead of having the copy constructor call, we have the move constructor called. And this move constructor, as we'll see, is going to be a lot more lightweight than the copy constructor, because what it's going to do is it's going to basically steal the values from something and just move them instead of copying them. And then likewise, you're going to see these destructors that are going to get called are also going to be very lightweight because they have nothing to delete. So let's go over here and let's take a look at simple string, and we'll see how its move constructor is defined. So remember, here's the old copy constructor. This copy constructor made a literal copy using new care and stir copy to actually copy the contents of the right-hand side into a new, fresh version of the left-hand side. So there was actually allocations and copying taking place. In contrast, look at what the move constructor does. It has this funny syntax. This is called an R-value reference, kind of a funny name. And what it's going to do is, rather than doing any copying at all, it's simply going to move the pointer. It's going to move the ownership of the right-hand side pointer to the left-hand side, to the guy that we're initializing. It's magic. No copying takes place at all. And then we go ahead and we set the right-hand side's pointer to be null because we just moved it. So it no longer has any ownership of this. And so as a consequence, this is blazingly fast because we're not actually doing any copying. And this is actually going to take place in a couple different places. And so what we're really doing here, if you go back and look at the running of the code, is we're creating this object here. So we've actually made it. We did a stir new there and did a copy of that from the const char star. But all of these calls are just basically moving or transferring the ownership of that pointer down to the final place where it goes into the pair in the point class. So once we allocate this once, we're just moving a pointer, and then we're disavowing ownership of the pointer by setting it to null in the move constructor. So that's way, 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 way faster. And you'll also notice in the destructor, notice it says null pointer. So if we go over here to simple string and we look at the destructor for simple string, you're going to see how what we do here is if we delete the stir underscore, because if it's null, that does nothing. It's just a no op. We could actually even avoid that altogether, but the very first thing delete does is check to see if it's a null. So it's pointless to do the comparison ourselves. But then just for diagnostic purposes, if stir underscore was the null pointer, we print out the fact it was a null pointer. So that means we didn't actually delete anything. And that's the other point to notice when you look at the output from this code, is that even though it looks like we're creating lots of these objects, they're just doing a pointer assignment, nulling out the stir underscore field, and then their destructor is doing nothing. So the key point of this is by being able to use the move semantics, which we're just conditionally doing here with a macro, just to go back and forth and show you the different variants. In real production code, I would probably just write that with STDMove and be done with it. But here I want to be able to show what happens when we can enable and disable this to see what the effect is on the overhead of the program. So by turning on the move semantics, even though we're passing these values we're passing the parameters by value to the point class. Remember, we're passing them by value here. We're actually just moving and transferring the ownership of the pointers. So it's much more efficient. And this is a very, very important tool to have in your toolbox when you start working with STL. You need to know how to use the move operations properly. And I should hasten to add that the existing containers and other classes in STL and the standard C++ library, for that matter, have all been revised and refactored to use move operations wherever possible in order to speed them up. So the reason why this was added to C++ is because obviously STL is heavily based on value semantics, and some really clever compiler writers and other language designers took a careful look at how to make C++ work a lot more effectively by using move semantics instead of having to only use copy, constructor, and destructor semantics. So those are the things that I had wanted to cover today. This particular example is a fun one. I strongly recommend you take some time to look at it and play around with it. Feel free to modify it as you see fit, to fold it to your will. And in future courses, we'll also take a look at, our future webinars, we'll also take a look at the move assignment operator, which basically has the same idea as the move constructor. You're passing the ownership from the right-hand side into the left-hand side without actually having to do a full-blown assignment and allocation and copy and so on. So that's what I want to cover today. Thanks everybody for watching the video. Please like and subscribe if you enjoyed it, and don't forget to follow me on Twitter. Thanks.